Let's look at the problem with the given that scenario. I want to calculate the probability that A occurs given that we're looking at B as a sample space. Now you see the picture here that I have. It gives both where A and B are located, but our sample space is no longer the entire normal curve. The new sample space is just B between 250 and 282 days. And what I want is the probability that I land between 266 and 282 days. Again, notice that the yellow area is what's common to both A and B, and the denominator consists of the probability of B, the new sample space. So what I'm going to do is calculate the probability of A given B in terms of the old probabilities in the old sample space. So again, in the old sample space, the probability of A and B is 34%. In the old sample space, the probability of B, since it's one standard deviation to the left and to the right, is 68%, using again the 68, 95, 99.7 rule. So the probability of A, given that we're only considering the sample space of B, is 50%. Notice again how the probability has changed from the old sample space. Let's switch this around. What's the probability of B given A? So now the sample space is A. Here's a picture of the new sample space between 266 and 298 days. You can pause this video and see if you can calculate this new probability, just like I did in the previous problem. Again, use the old sample space. Again, using the old sample space, the 34% stays the same, the probability of A and B, just like in the previous problem. But the probability of A between 266 and 298 days is half of 95%, since 298 is 2 standard deviations to the right. That gives me a probability of 71.58%, which you notice is different from the half we had before. The moral of the story is, yes, it does matter what the sample space is. If you switch those two symbols, you do not get the same probability.